Welcome back to bilingual e-lectures for diploma students, unit 5, lesson 2, steel structures. And in the previous class we have seen that design of a tensile member when it is subjected to a rupture or the failure takes place in the net cross sectional area. And for example, if a plate is subjected to tensile force, then the net area, how to calculate the net area of the plate which is having a row of holes, and this is an example, of course illustration, and these are all the application of tensile forces. And let me say the cross section of the plate is B and the thickness of the plate is T, breadth of the plate is B and the thickness is T, and the holes diameter is denoted by D suffix H, and this is the column of holes 1, 2, 3, 4, 5 etc. And the net area is calculated like this: from the breadth of the plate you deduct the diameters of number of holes, that is all, and you multiply that by the thickness of the plate, that will give you the net area. In other words, A n net area is equal to B minus n times of the diameter of the hole. DH stands for the diameter of the holes, and which is multiplied by the thickness, which will give you the net area of the section or the critical section. And if suppose if the plate is having holes in a staggered manner, and the horizontal distance between the holes is denoted by Ps, and the vertical distance is denoted by a letter G, and where the Ps stands for the pitch distance and the G stands for the gauge length distance, and DH stands for the diameter of the holes, and of course B denotes breadth of the plate, and T, of course this is the front elevation. So, T is the thickness of the plate, and net area of this type of plate which is having holes in a staggered manner, that is given by B minus n times of DH plus summation of P square S by 4 G, the whole multiplied by T. So, that will give the net area of the plate which is having holes in a staggered manner. And the second component in tension member, it is a single angle, and of course this is the gusset plate and this is the angle, and this leg is connected. Of course, you know angle is having one vertical leg and the other one is called a horizontal leg. Here a leg which is connected to the gusset plate is known as connected leg, and which is a leg which is not connected to the gusset plate is known as outstanding leg or unconnected leg. And for this type of angle, a single angle which is connected to the gusset plate through nut and bolt or by welding, the net area is governed by this equation. Here Tn, that is design tensile strength of the tension member, that is angle member, is equal to, again remember this is tensile strength, and I told you tensile strength is nothing but the load carrying capacity. Again load is equal to area into stress. So, this part you just remember 0.9 times of net area of the connected leg multiplied by the ultimate stress. Always the net area is associated with ultimate stress, and which is associated with the partial safety factor for the material under ultimate stress. So, this is the area into the stress. Area into stress will give you the load, it is nothing but the tensile load carrying capacity, plus this is the connected leg and the other leg is there. This part is the connected leg, and here this is the connected leg, and this one is the outstanding leg. Outstanding leg is also contributing for the tensile load carrying capacity. So, the outstanding leg, gross area of the outstanding leg, and again gross area is also always associated with yield stress. So, gross area of the outstanding leg, yield stress, and which is associated with the partial safety factor for the material under yield. So, again this is area into stress, area into stress will give you load, and this part of the equation will give you the tensile load carrying capacity of the connected leg, and this part of the equation will give you the tensile load carrying capacity of the outstanding leg. So, these two combined will give you the total tensile load carrying capacity of the single angle which is connected by means of bolt or welding through a gusset plate. And again there are certain letters which will indicate symbols. ANC stands for net area of the connected leg, and again AGO stands for gross area of the outstanding leg, beta, this is the factor which is to be multiplied for the calculation of outstanding leg, strength of the outstanding leg. 1.4 minus 0.76 into W by T, where W is the length of the unconnected leg. This is the length of the unconnected leg shown in the image, and this is the length of the unconnected leg, and the thickness of the leg. Again, Fi is the yield stress and Fu is the ultimate stress. Bs is the shear lag distance, which is calculated for the bolt and nut connection, which is the distance between the topmost edge or the outermost edge of the unconnected leg to the connected point. The connected point here is the bolt. So, for this type of single angle connection, the shear lag distance is calculated from this point, center of this bolt to this edge. So, therefore, this is equal to W plus W1. So, Bs is equal to W plus W1. For here, can write here it is Bs is equal to W plus W1, whereas here it is Bs is equal to W. So, shear lag distance, this is very important for the calculation, and LC, this is the length of N connection, and again this beta value, you have got the minimum value and the maximum value as well as the actual beta value. So, minimum is 0.7 which is prescribed in the code, and the maximum value is the ratio of the stresses Fu into gamma m naught divided by Fy into gamma m1. So, that is how you have to calculate the net area for tensile member under rupture. And the third mode of failure is design tensile strength against block shear, which is denoted by TDB. And for this, I want to show you some image which will, I think which will give you a clear picture of what is happening if a member is connected to a gusset plate. Now, you can see, as you can see, this is the angle, right, this is the angle, and of course, this is an unequal angle, and this is the gusset plate, and block shear of course, which will occur. Now, listen, yes. Now, this is the arrangement, and this is the angle, length of the angle, this is the thickness of the angle, this is the outstanding leg, and this is the connected leg. And if this member, and this is the gusset plate of course, this member is subjected to tensile force, a pulling force in this direction, this area of the connection as well as this area of the connection, I have denoted this as 1, 2 and 3, 4, which will be in shearing plane. This area as well as the bottom area which is connected to the gusset plate will be in shearing plane, and the perpendicular to this shearing plane will be in tension plane. So, this and this will be in shearing plane and this plane will be in tearing plane. Then that means shear, one assumption is the shearing will yield, and in tension it will fracture. Again I repeat, shearing area will yield and tension area will get fractured. The other assumption is this: shearing area will get fracture and the tension area will be in yielding. So, you have to calculate 2 times for the design strength against block shear. First, you assume shear yield, tension fracture. Second, you assume shear fracture, tension yield. So, and remember, this is the shearing plane and this is the tearing plane or tension plane, and the failure will take place for this image. This will take place along the route 1, 2, 3, 4. So, this is 1, 2 will be shearing and 3, 4 will be shearing and 2, 3 will be in tearing or tension. Similarly, here this is 1, 2, 3, 4 again, 1, 2 will be in shearing, 3, 4 will be in shearing and 2, 3 will be in tension. So, horizontal direction there will be a shearing plane, and in the vertical direction there will be a tearing plane or tension plane. And design tensile strength of the member against a block shear is given by this expression TdB. Again this is the multiplication of area and the stress. This is AVG and this part is in yield and this part is in fracture. Shear plane is in yield now and the tension plane is in fracture. So, yielding means always it is associated with the gross area and the yield stress, and the partial safety factor for gamma material under yield should be multiplied by root 3 for shear. In general it is divided by Fy is divided by gamma m naught. Since it is in shear, this partial safety factor should be multiplied by root 3, and again this is the area and this is the stress, again gross area, yield stress. So, this will give you some amount of load, and the other part, this is 0.9 times of ATN. ATN stands for the net area in tension, again net area ultimate stress, net area ultimate stress, gross area yield stress and net area ultimate stress. So, net area is an ultimate stress and which is associated with the relevant partial safety factor. Again area into stress will give you some amount of load and area into stress will give you some amount of load, and these two loads will comprises of the total design tensile strength of the member against block shear. Again this is shear plane in fracture and tension plane in yield. This is the net area in shear. So, when I say net area, it should be associated with the ultimate stress. Again shear, this is gross area always associated with yield stress. So, this we have to remember, and the desired requirements, of course it should not be less than, that is the design strength of the member should not be less than the factor to design tension to be obtained from the analysis of the structure. And design procedure, you select a suitable section based on the permissible tensile stress, usually which is assumed as 0.9 times of Fy yield stress or 0.6 times of ultimate stress or Fu. And after selecting the trial section, we have to check for the load carrying capacity of the tension member. So far we have seen the modes of failures of tension member and how to ascertain the value of design strength of a tension member, and which is governed by yielding of gross section TDG and against the rupture of critical section TDN, and the last one against the block shear TDB. So, design tensile strength of the member is the lowest or the least of all these three values, namely TDG, TDN and TDB. So, we will quickly go into the worked out examples. So, this is an example, a plate which is subjected to a tensile force, and you are asked to calculate the design tensile strength of the plate, and the material property Fy is 410 Newton per millimeter square, and the cross sectional size of the plate is given as 120 mm by 12 mm, which is having 4 holes of diameter 22 mm, and these are all the data given. And of course, this is a small image which is to illustrate the given section. Of course, this is the plate of breadth 120 and which is having 3 holes in a single column, diameter of the hole is 22 mm. And now these are all the data given, of course, and you are asked to calculate the design tensile strength against yielding as well as design tensile strength against rupture of critical section. And since you are not given the connection details, you cannot go in for the third mode of failure. So, I will restrict the solution to mode of failure 1 and mode of failure 2. So, first mode of failure or the design strength against yielding of cross section TDG, and this is the expression to be used to calculate. TDG is equal to gross area of the member into yield stress, and this yield stress is always associated with the partial safety factor for material under yielding. So, gamma m naught. So, area, again this is the stress, area into stress will give you the load or the strength. Now, this is the cross area of cross sectional area, gross area of the plate 120 by 22 and the partial safety factor, and the TDG value is worked out as 327.27 kilonewton. And the second mode of failure, of course, the strength against the second mode of failure is TDN is equal to 0.9 AN Fu by gamma m1. Again this is a load, it is the area into stress. Again net area is associated always with ultimate stress. So, net area of course, since the plate is having holes, we have to deduct the area of the holes. So, net area after deducting the area of the holes is found to be 1176 millimeter square. Of course, this is mistakenly typewritten, it is the power 1176 millimeter square, and the design tensile strength of the given plate against rupture of the critical section is found to be 347.155 kilonewton. And the design strength of the member is the least of these two. First one is 327 and second one is 347. So, the lesser value is 327, and therefore, the design tensile strength of the member is found to be 327.27 kilonewton. It is a very simple example, and of course, it is a plate member. And in the second example, we can see a plate which is subjected to tensile force, but having holes in a staggered position. So, the pitch of the holes is given as 55 mm PS, and the gauge of the holes is given as 45 mm. Diameter of the holes is given as 22 mm, which is having 3 holes. And the cross section of the plate, of course, it is given as 210 mm is the breadth, and the thickness of the plate is 10 mm, and the mechanical properties of the material is given as Fy yield stress and Fu ultimate stress. And we are going to find out the design tensile strength of this plate. And again, design tensile strength TDG denoted by TDG is equal to area into stress. It is gross area, so denoted by AG. Gross area, I am repeatedly saying gross area is associated with yield stress. So, AG into Fy, which is associated with the partial safety factor gamma m naught. So, by substituting all the relevant values, we get the value of design tensile strength against yielding TDG is equal to 477.27 kilonewton. And for the same plate, the second mode of failure or strength against the second mode of failure is TDN, and rupture may takes place. We will go back to this image. So, rupture may take place in the root. I have written here, this is 1, 2, 3, 4 and 5. So, the rupture may take place along the root 1, 2, 3, 4 and 5, this is 1, and the other option, the rupture may take place along the root 1, 2, 4 and 5. So, we have to calculate the net area along 1, 2, 3, 4, 5 as well as 1, 2, 4, 5, then we will take the lesser area into account. So, by doing so, the lesser area is found to be, of course, A and C is found to be 1692.08 millimeter square, and substituting the relevant values will get the design tensile strength of the given plate against rupture of critical section is 490.032 kilonewton. Again, the design tensile strength of the member is the lesser of these two. So, the design tensile strength of the plate which is having the holes in the given exercise or given example is found to be 477.27 kilonewton. And slowly we will get into the real picture. Of course, it is a single angle connected to a gusset plate, and that two end connections are given, and we will go through this example, and which is of designated as ISA, Indian Standard Angle of 100 by 65 by 10, used as a tension member, which is connected at its ends to a gusset plate, and the dotted line shows you the gusset plate, and this is the angle, and the gusset plate thickness is 8 mm, whereas the angle thickness is 10 mm, and which is connected to the gusset plate. And we are asked to calculate the design tensile strength of the angle, and the mechanical properties of the material is given. Length of the weld along the length direction is given as 115 mm. This is nothing but the length of connection, and these are all the data given. We will quickly go through this and we will do the calculation. So, the first mode of failure, that is the strength against yielding of gross area TDG is equal to AG into Fi divided by gamma m naught, and for the given Indian standard angle we have to take the value of AG and other parameters, geometrical parameters, from the available steel table, right. So, AG from the steel table is found to be 1551 millimeter square, and Fi it is given, gamma m naught we are supposed to remember this value 1.1, and by substituting all these values we will end up with the design strength of the given single angle due to yielding of gross area 423 kilonewton. And the second mode of failure or the strength against the second mode of failure TDN, which is given by this expression and this expression is available in the handbook as well as in the code book IS 800 2007, and this is for the connected leg and this is for the unconnected leg or outstanding leg. So, we will slowly calculate the parameters which are required to substitute. So, area of the net connected leg, this is nothing but the breadth B and this is T, B minus T by 2, here I can write this is A and C is equal to B minus T by 2 into T, that is all. It is very simple expression. Now, B is the breadth of the leg, of course it is given there, and 100 minus 10 by 2, 10 is nothing but the thickness, B minus T by 2 into T, that will give you the net area of the connected leg, and this is the gross area of the connected leg. This is mistakenly written, of course, this should not be a multiplication here, this. So, 65 minus, just replace this multiplication symbol by subtraction symbol, 65 minus 10 by 2 into 10, that will give you the gross area of the outstanding leg or the unconnected leg, and the value of beta again 1.4 minus 0.076 W by T Fy by Fu into Bs, where Bs is the shear lag distance and Lc is the length of the connection. And again shear lag distance, of course we have to calculate. For this, the shear lag distance is measured from the top of the outstanding leg to the connection point, and therefore W is from this point to this point. So, W for this exercise is 65 mm. So, substituting the relevant values, we get the value of beta as 1.209, and the permitted value of beta is, by using this expression, is found to be 1.290, and we know that the minimum value of beta is 0.7. So, the beta whatever that we have arrived is within the limit, which is greater than the minimum and less than the maximum. So, we will use the same value of beta here and we will try to calculate the design strength of the member under rupture of a critical section. By substituting the relevant values, it is found to be 498.796 kilonewton. So, this is the strength against rupture. This is very important, because since you are given the connection details, you have to find out the design tensile strength of the member for block shear. Again you have to predict which one is the shearing plane and which one is the tearing plane, right. So, the connection may fail due to shearing of gusset plate along 1, 2 and 3, 4, and simultaneously the tearing of gusset plate along 2 and 3. So, and accordingly we can arrive at the area of the sections. This is the gross area or net shearing area denoted by letter AVG and AVN, and in this sketch you can see that 1, 2 and 3, 4 are the shearing plane. Similarly, 2 to 3 is the tearing plane. Now, we will take shear plane in yield and tension plane in fracture. So, accordingly we will calculate the areas. So, shearing area is found to be, and shearing area is 2 times, because at the top as well as at the bottom. So, 2 into the length of connection is given as 115. So, 2 into 115 into the thickness of the gusset plate. So, that is 8. So, the area comes as 1840 millimeter square. And gross area, I mean net area or gross area in tearing means fracture, கிழியறது. So, இப்படி நீங்கள் force இப்படி apply பண்ணும்போது என்னாகும், இந்த 1, 2 and 3, 4 shear ஆகும், perpendicular to that fracture ஆகும் இல்லை கிழியும். Now, tension area, of course fracture area is, this is 100 into 8 is 800 millimeter square. Again I am repeating, 1, 2, 3, 4 are the shear plane, 1, 2, 3, 4 are the shearing plane, and 2, 3 is the tension plane. So, we will first take shear plane in yield and tension plane in fracture, very simple. Again we are going to calculate the strength, of course load. So, we know that load is the product of area and stress. This is the area and this is the stress, because shear area is in yield. So, again area into yield stress and divided by the relevant partial safety factors, that will give you the load. And again this is the tensile load. So, this is the area which is under fracture or tearing. So, we will take the net area and the ultimate stress. Again net area is associated with a coefficient 0.9, 90%. So, this part will give you the shear yield and this part will give you the tension fracture. In total, for the first option, the design tensile strength due to block shear is found to be 543.165 kilonewton, and the second option is the shear plane is in fracture and the tension plays in plane is in yield. So, since it is in fracture, we have to take the net area and the ultimate stress, that is a simple. So, this is net area and the ultimate stress and associated with the relevant partial safety factor. This will give you the load for this part and this will give you the strength or load for this part, that is tension in yield. Again yield, I said yield is always associated with the gross area. So, ATG into Fi, and yield stress is associated with the partial safety factor for material under yield gamma m naught. So, substituting the relevant values, we get the second option against block shear as 554.726 kilonewton, and design strength against block shear is the lesser of these two. So, that is found to be 543.165 kilonewton, and design strength and intention of the member is the least of TDG, TDN and TDB. So, the least is 423 kilonewton, and therefore, the design tensile strength of the angle is found to be 423 kilonewton. And we will have a similar type of problem. There we have connected a longer leg, and in this exercise the angle is connected with a smaller leg with the same data tank. So, in the similar way we have calculated the design tensile strength of the given member against yielding. This is 1000, area, gross area is 1005. Of course, all these values are available in the handbook. Substituting the relevant values, we get the design strength of the member under tension is 423 kilonewton, and design strength against rupture of the critical section for this case is found to be 418.08 kilonewton, and against block shear, which is found to be 416.67 kilonewton, and the design strength of the tension member is the least of all these three options 1, 2, 3, namely TDG, TDN and TDB, and which is found to be 416.67 kilonewton. I have mistakenly typed here, which is K should be in smaller case, lower case, and N should be in upper case. I will make the corrections. And to summarize the design of tension members, the points or the key points or the key words that we have to remember is gross area yield stress, net area ultimate stress, and again yield stress is associated with the partial safety, relevant partial safety factor. This is point number 1. And point number 2, when we do the calculation on design strength of the block shear, we have to know or we must know the planes in shear and the planes in tension. So, planes in shear first yield, then planes in tension will fracture, vice versa. There are two options. You calculate for both the options, find which one is the lesser one, and among all these three options, that is TDG, TDN, TDB, you find which one is the least one. That will give you the design tensile strength of the given member. Thank you. We will continue in the next session. Thank you.